In the back, can you hear me? Yeah, okay. So this is, I guess, a 3-lecture series on scientific computing with Python. And it's going to start very basic, and then we'll get progressively more scientific, but it's going to start really just with Python. And it's supposed to be interactive. So how many, I'm going to do a couple polls before we start. So how many people have a device, a computer, an iPad, a phone? It'd be kind of hard, but you could do it, with them with which they can connect to the network right now? Okay, how many people don't? Anybody? Oh, okay, one. Okay, well, if you don't have it, you won't be able to do the interactive stuff, so you could try to borrow one or look on with somebody else, but it looks like most people do. That's good. That's step one. Now, before we actually start getting everybody connected, though, how many people already program in Python? Wow. OK. How many people have never used Python at all? OK. And how many people of those, how many of you have never programmed at all? One. OK. So good. That wasn't supposed to be a shaming moment in the class, but you look like you don't mind. Oh, I'm a theorist. Oh, no. Come on. Even the greatest theorists of our time built their own computers back in the day. So, well, it seems like this lecture may be, for many of you, then a little bit basic, because today is going to be really just introduction to Python, a couple of high-level words about why I think it's a good language for scientific computing, and then just like, what's the basic syntax, how to use Jupyter notebooks, how do you do some very basic things and use the basic data structures and flow control. And if I apologize if you already know this. If you have insightful guru-level comments to make, to provide us with, you're welcome to do so when I'm not here. And you know, impress your friends that way. That's fine. For the people who, I think this is geared to a level of mostly people who've programmed but maybe don't know Python. Hopefully you'll be able to absorb everything you need to know about the basics of the language in one lecture. Tomorrow, we'll do a tour of some basic functionality of NumPy and SciPy, which are numerical packages, and that'll end with doing some sparse matrix calculations in class. And the last lecture, we'll talk about sort of principles of how to optimize a scientific code, and we'll do it with Ising Monte Carlo as a running example. So that's sort of the plan for the 3 lectures, and it's supposed to be interactive. So to get the interactive going, I want everybody to open your browser. Hopefully it will work in any modern browser. And you can go to the website, type into the address bar, HTTPS, here, I'll even write it. Let's see if I can do this. Jupyter.ictp.it. Now, you all can read that, right? Here, let's make that a little bit bigger. How about that? I think I spelled it right. Don't miss the S. It won't connect if you don't use secure HTTP. This is a server that we set up. It has not been stress tested for 180 simultaneous users, so everything might explode right now. Hopefully, once you've gone there, you see this page. Is it working? Yeah. Is it not working? Wow, amazing. OK, now you need to log in with the ICTP credentials that were given with your ID. Mine are there. Oh my God, you can see the blocks of my password. If you count really carefully, you'll be able to figure out that it's the same length as all of yours. Now comes the moment of truth as the poor server simultaneously creates 180 user accounts. Let's see if it works. Oh, really? Great. Yeah, if the computer crashes, then, well, it won't be interactive, will it? This is not very promising. Has anybody seen more than this yet? Oh. Your server is starting up, good. Mine is not. Aha, great. So most of you won't have the stuff in there, but has everybody gotten to a screen that looks kind of like this? Okay. Wait, I should do hands again. Is there going to be like a wave? Put up your hand if you've gotten there. Oh, wow. Okay. Yeah, it's struggling, our poor server. It should not matter if you're on EGU Roam or ICTP Secure or ICTP Open. It's an internet-facing server. Yeah, but then I have to distribute the notebook, and this is much better. I mean, some of you, it's true, we could do that, but let me start talking, actually. I can start going, and I'm going to tell you what to do, and for the first bit anyway, I'm just going to blah, 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 so it doesn't really matter if you've loaded it. Hopefully by the time we get to an interactive bit, everybody's will have loaded. So what you're going to do once you get there is you click on this Examples tab, and you should see, hopefully, this Intro 2018 ICTP notebook, and then you go to Use, like that, and then fetch a copy, and if we're very lucky, you'll see this. And that will then be your very own copy of this beautiful notebook, which I wrote just for you guys, okay? Don't you feel special? Oh, fine. So we're gonna work through it. This is actually Jupyter. That's what it says up top. And it's become a sort of standard interface for doing interactive work in Python. And that's, you guys are all logging into Jupyter clients of your own running on a server. It's kind of an interface a little bit like a Mathematica notebook. You have a mixture of code and comments and output from calculations all in one thing, which you can save and which you access through your browser, even if you're running it locally. We didn't have you set it up locally because it's a lot easier just to get going with everybody on the same server. So we'll explain more how to use it as we go. What is this course? So it is a short crash course on Python, computing with Python, scientific computing with Python, my flavor of computing with Python. As I point out at the top here, and I have a few links, if you really want to learn Python, you should just sit down for a day or two and work through some of the tutorials available on the web. I've got links to some good ones which have a scientific flavor. Some of them are longer, some of them are shorter. One of the reasons that Python is a great language to work with is that it is very widely used. So it's kind of circular. You use it because it's used, right? But that's actually a really good reason. It means that there's a lot of documentation. Google is your friend. You will find anything you want to do with a little bit of searching, and you can find your feet that way. And there's also lots and lots of libraries available. So let's just sort of talk through that a little bit. So why Python? This is my soapbox period. So why Python for scientific computing, right? So it's a simple, well-structured general purpose language. It's very readable. Unlike many other languages, white space matters in Python. So basically, how many of you know about, what is it, the obfuscated code competitions? Has anybody submitted anything? this like too old for you guys? Don't they still run? No? Does anybody know what obfuscated code is? So you write a sequence of symbols that turn out to be a C program when you squint at them. And they do something really miraculous, but you have no idea when you look at it what the hell it was supposed to do. Okay? And there are competitions for who can write the most miraculous programs in complete gibberish, right? But this is very bad for doing science. Why? Because you finish your miracle late night work and you get this cool program, and then you come back to it a couple weeks later and you're like, what? And forget about it a few months or a year later. That's you. And if you send it to anybody else, they don't know what you did anyway. So nothing's reproducible, and you can't really understand what you did. So Python kind of forces reasonably good habits on you in how you write your code to make it more readable, make it long-term, maintainable, understandable, debuggable. It was actually invented by Guido van Rossum as a teaching language, and that's why it has that kind of structure built into it. It's a high-level language, so you can do high-level things with just a few lines of code. That should help you rapidly develop or explore a problem. You don't have to write lots of code just to tweak parameters or play with different ways of looking at a model or something like that, different ways of doing a calculation, because it can do a lot of that for you. It's interactive, as we'll see. So again, that makes it faster to explore things. There's no need to compile, run, debug, revise, compile, which is the standard protocol for compiled languages. And you can do your data collection, or if you're doing numerics generation, analysis, and publication plotting all in the sort of scientific Python world, which makes it very convenient to go from exploration to production collection to paper figures, right? Which is, of course, the only thing we actually produce around here. So then, in terms of speed, some of you will sniff and go, but it's an interpreted language. How could it possibly be fast enough for the hardcore numerical computing that I want to do? And the answer is, it usually is. It is not always. But for most purposes, it will be plenty fast. And the main thing to remember, and we'll discuss this a lot more in the third lecture particularly, is that your exploration time, your development time, is way more important than CPU time. So getting the right ideas and the right calculations and the right algorithms in place, which you can do within Python more rapidly, is more important than getting an extra factor of 5 or something from the compiled code. And usually, if you really need to, you can swap out sort of the bottleneck code for a compiled language when you get to that stage in a project anyway. It's not hard to do. So that's why speed isn't usually a problem. I already mentioned there's a vibrant community, so lots of online documentation. It's open source. You don't have to pay for it. Steve Wolfram isn't getting your money. I mean, he's a great guy, but he has a lot of money. And then there's an extremely rich range of scientific computing libraries and toolkits which allow you to do all kinds of things without reinventing the wheel. Now, when you are a graduate student particularly, or whatever, you're a student, and you are first playing with doing some kind of calculation, actually reinventing the wheel is an extremely useful thing to do, because then you understand how the wheel works, right? But once you get past the basic wheels, you don't really usually want to use that version. It's much better to just go ahead and use mature versions of whatever kind of algorithm, fast Fourier transform, whatever it is, that are available in mature toolkits, right? So there's a learning aspect while you're exploring and you want to reinvent the wheel. That's OK, and you can do that in Python, and then you can just swap out your kind of, your pedagogical stuff with actually getting stuff done with mature libraries. So that's my 2 bits on that. So I had an argument yesterday over dinner over what constituted pure Python. And the answer, there's 2 answers. There's what's the core sort of functionality of the language that you would get if all you did was install Python and start programming and using the basic data types. And actually, that's most of what we'll talk about today. But I think that it is perfectly fair to say that any of the what have now become very mature standard scientific libraries are pure Python. from our point of view. There's no point in making a distinction. If you can use the toolkit and it's mature and reliable, you should use the toolkit. And in particular, these are the main components that you use in a scientific setting. So the core pieces of the platform are Python itself, which is the language interpreter. It has some standard data types. We'll go through them today. Python is under development, so there are versions. Python 3.7 is current. Use it. There's an old version, Python 2.7, which is slightly incompatible. It is almost 10 years old and will no longer be maintained in 2020, so don't use it. There's no reason to use the older version. Then there's this Jupyter, which is what we're using here, this notebook-based interface. I'm a big fan of these. I actually do research with Jupyter notebooks all the time, like stuff that I'm working on that will turn into real science, because it gives you a nice framework to keep track of code and output and comments and everything in one place. So that builds on something called IPython, which is just the interactive Python shell. This interface gives you interactive manipulation of plots. We won't talk about it, but it's easy to use basic parallelization. If you have a bunch of computer cores available and you want to farm out some computation, you can do that using notebooks and Python pretty easily. Lots of use for extra bells and whistles. So then the three key libraries are NumPy, which is kind of the baseline for doing scientific computing. It is a library which provides numerical array objects and routines to manipulate them, and some basic linear algebra. And then SciPy, which is scientific Python as opposed to numeric Python. It's a set of libraries built on top of NumPy which do provide a lot more sophisticated scientific tools. Signal processing, numerical function optimization, ODE integration, all kinds of things that you might want to do are provided by SciPy libraries. Then plotting, the primary plotting library, there's some other ones, but the primary one, which is what I use, it works very well, is very mature, is called matplotlib. It does really publication-ready 2D plots. They're beautiful. And you can do basic 3D stuff as well. That's getting better. There's some other 3D plotting libraries if you're into 3D plotting that you would want to investigate. And then I'm mentioning, we're not going to use it at all in the course, but these last two, Pandas and MayaVI. MayaVI is one of the other 3D visualization tools. If you need to do it and do interactive things in 3D, then MayaVI is something to look into. And Pandas is a library, it's relatively new, which provides a layer of data structures above NumPy again, which are richer and they're quite useful for doing sort of analysis of heterogeneous data, relational data and things like that. It's kind of like a data structure that provides you something like an Excel spreadsheet programmatically. So that we won't use in this course, but actually I find it sometimes useful to use as well. So I've talked for a few minutes. How many people have gotten to the notebook page? Good. Has anybody not gotten to the notebook page? 1, 2, 3, 4, 5. It's just stuck? What's that? It's loading still? You can try to reload and see if it goes. It's still OK. I can talk a little bit more, so hopefully you guys will come through. But at this point, we're getting close to where you actually will want to be able to do stuff, right? So there are two primary ways. This seems like crazy. I'm like telling you how to do workflow. I feel like some like business consultant or something like that. But you know what? Let's be practical. Let's just get stuff done here. So anyway, there's two primary workflows for working with Python. One of them is work in a Jupyter notebook, write code in cells, analyze, plot, et cetera. Everything in that case is stored in a .ipynb, or IPython notebook file, which is what we are looking at. We are looking at an IPynb file. Or the kind of more traditional way to do things before this interface was write your code in .py files using a text editor and run those either from the shell or within, or actually within the IPython notebook, you can do that as well, or some other terminal, and output files with your data and things like that. And we're not going to do that, but you can. And if you're doing things that actually get programmatic and you want to push onto clusters, then you'll have to start tying your code up in .python files. Okay? So we'll stick to the first. Well, I guess I'm kind of just reading my notes here. So I'll come over here. And I can read it. While you're using a notebook, there is a kernel running which actually executes your commands and stores your variables. So that's a bit like Mathematica. You can quit and restart the kernel, and it will forget everything it had in its head. But anything that's visually displayed in the notebook will still be there until you overwrite it, okay? And savable. So that can be done from this kernel menu. You see restart and clear output, restart and run all. These are things that will kill the kernel in the background, which is storing whatever you've told it to store, okay? Resetting things is often quite useful. You can check that your code actually is doing what you want. If you go back and forth in a development process, you might have set things later than you needed them. And so it's useful to go back and make sure you're actually calculating what you think you're calculating. Or if things just get screwed up, sometimes it's useful. Okay. This footnote is not so important. .py files are called scripts if they consist primarily of a sequence of commands to be run, and modules if they're basically libraries containing a bunch of functions that you want to import and use in something else. So module is the Pythonic term for a library of functions that you can call. Okay. Notebook usage. Now, how many people have used VI? How many people actually like using VI? It's okay. If you don't know VI, that's good. You'll be happier for it. So in the bad old days, when there were no things like the web, and you had a terminal that you had to do all your editing in, you did command line editing. And to do editing of a text document, you usually had two modes. You had a mode where you could actually edit the text, and a mode where you would issue commands, which were things like find this, or replace this, or add a line there, that kind of thing. So there's an edit mode and command mode. VI has an edit mode and command mode. It actually has been around since those bad old days, with apologies to the VI aficionados here. I actually use it sometimes. The notebooks actually also have a command mode and an edit mode. And right now, unless you guys have hit keys, I think you will be in the command mode. So in particular, if I press H, it didn't type an H into a box. It popped up a help panel, right? And this tells me keyboard shortcuts that I can use mostly in command mode, right? And I can scroll and look around, and there's all kinds of things here. Great. Command mode is useful. That's how you move around and interact with cells as blocks. You can delete them. You can cut, copy, paste, whatever. You can move them around. You can use Shift-Enter to execute them. I'm going to execute this cell. It didn't do anything because it was just a comment anyway, but I did it. And if I'm in edit, and I can use Enter to go into edit mode, and now I can edit my text, which it was rendering for me. And I could say, press escape to go to command mode if you really want to, like that. And then execute, and it re-rendered it. And where'd it go? Press escape. There it is, right? Here, I'm going to use this pointer they gave me. If you really want to, is what I just typed there. So I'm belaboring this because it's a pain until you get it. Right? Once you know there's a command mode and an edit mode, then working with these notebooks is very fast. If you get confused about that, then you will be confused working with the notebooks. Okay? In editing mode, so there's Shift-Enter always executes the current cell. There's actually two kinds, before I say what these are about, there's two types of cells. There's what are called markdown cells for notes. And you can see up here, this dropdown tells me it's a markdown cell. And that's like this one, which was just full of comments. And then there's code cells, which are the things you can execute. And if you're in a code cell in editing mode, then pressing tab will invoke autocomplete. Pressing shift tab will bring up help. Now, every object, function, whatever, in Python has help documentation attached to it, which is interactively available. This is part of why it is a good language just to get going with. Okay? So I'm belaboring it, but shift tab and tab are your friends. You want to use them. Okay? So anyway, now we have the first official exercise. Try editing this markdown block to make it more interesting. Go! Who can make it the most interesting? The one that says this one. I don't hear a lot of clicking. Oh, man. Modern keyboards are kind of mushy. Is that what this is about? Okay, I'm going to make it more interesting. Help your neighbors if there's problems. So, did everybody make it more interesting and then manage to shift enter in order to re-render it? Yes. Okay. Very good. So, some of you will see that one thing that it supports, which is useful scientifically, is that in markdown blocks, you can use math symbols from LaTeX just for notes to yourself. And it is exactly LaTeX syntax. So if I put in these dollars and dollars blocks like that, they will render nicely. So this is useful for making notes to myself or making a notebook that I could share with collaborators or something like that, which explains some analysis, does some computation, does some plots, all in one place. Okay? So now the next exercise, execute the next block, then create a new block, type x dot, press tab, and shift tab, and just see what happens. I'm going to give everybody a minute to do it. I mean, I am. So we executed it. I'm creating a new block by pressing A. Oops. So you can create a new block by pressing A from command mode, or B. A will create it above where you're currently pointing, and B will create it below. So if I create A, then I hit enter to go into it. I press X dot, tab. Blah! And that's the autocomplete. So this symbol X, which is a variable containing the number 10, has a bunch of methods on it, and autocomplete knows what they are. Okay? So tab, very useful. You can investigate what you are playing with. And if I hit shift tab, and I hit it again, and I hit it a third time, I will get, oh, go away, a help block. So this is giving me lots of information about that symbol X. It's an int, its string form is 10, and if I call these int functions, it will convert a number of string to an integer. It tells me how to do other bases if I want to represent things in binary, 0b100, et cetera. And I can close this by clicking on the little X. These two things, shift tab and tab, very useful. Memorize them. Okay? Again, this is part of why Python is nice to work with, is because everything is available and there's documentation everywhere. Okay? Now, let's run this stuff. So what's going to happen? I know for some of you this is like really kindergarten stuff, and for some of you it's kind of new, but what's going to happen? hello world. Oh, it printed it. And what about this? It's the same. There's a small difference. One of them, wrong button. One of them, it printed, that's output. One of them, it's actually just showing me the value of this string, which was the last thing in the cell. Okay? So that's a string. 2.5 times 3. Wow, a bunch of scientists here, and you guys can't multiply? It's embarrassing. 3 to the third. 27. 3 plus 3, 6. What's AB plus CD do? We're using it as a calculator. If you get nothing else from this, you'll know how to use Jupyter Notebooks as a very heavy-duty calculator. So what does this do? What's it going to output? Plus, when applied to numbers, we'll add them, and when applied to strings, it will concatenate them to make bigger strings. Okay? Easy. And finally, just a note that Python doesn't, those two strings are equal, even though I use different quotes. The quotes introduce the string. The fact that it's single or double doesn't matter. Okay? Okay. Now, variables and objects. Maybe we're getting somewhere interesting. Everything in memory in Python is an object. Every object has a type, such as integer, string, ND array for NumPy arrays. Variables reference objects. They can reference objects of any type, and that type can change. Okay? So it's not like a typed language like C, where you have to say that some variable is a char or an int or something like that, and then for the duration of the program, it always refers to a char or an int. A variable in Python can refer to anything. So here, for maybe the one person who doesn't program, equals doesn't mean equals in programming, just as a general rule. It means assign the thing on the right to the thing on the left. Okay? And so A equals 3 assigns the integer 3 to A, which we can see if we just type A and look at the output. That has a type, int. A plus A is 6. 2 plus A is 5. And now, without declaring anything, I can just assign an array to A. Oh, oops. Ha! The first bug in my notebook. I haven't actually imported the NumPy libraries. So, fine. So, everybody, create a new cell. And then we will do the lazy way of doing this, %pylab inline. I wasn't going to have any actual scientific stuff until the next lecture, but I put this in here and forgot. So if I do that, then that basically loads the NumPy and matplotlib namespaces and will make array available to me. So we'll talk about that more tomorrow. But now I can use it. So A is now an array. The type of A is an ND array. A.shape. What does that mean? What do you think the shape of A is? It says 2 comma. Yeah, so the shape of the array, an array is actually an arbitrarily many-dimensional rectangular grid of numbers. In this case, it is just a one-dimensional thing, so it only has a length, and that's 2. So 2 is the shape, 2 comma. Okay. A plus A, it added these 2 row vectors, A and A, to itself, gave me 2, 4. 2 plus A, what did that do? Sorry, what? Yes, it did do broadcasting, but let's leave that aside for the moment. It added 2 to each element. You're right. Good. And now I can go ahead and say A is hello world. It's a string. Uh-oh. And the server goes down in fiery mess. Ah, yes. OK, so what's the type of A? It's a straw. A plus A. hello world, because plus for strings concatenates. What about 2 plus a? What's that going to do? It's wrong? What's that? It's going to blow the server up. OK, let's see. Well, I don't think it blew the server up, but it indeed threw a type error. And it said, basically, I can't add a string and an integer. That doesn't make any sense. And Python gave me a nice descriptive error message. Don't do that because of this, right? OK, good. So just a comment there. This is called operator overloading, which is that the plus symbol is an operator. And it can mean different things depending on what you try to apply it to. In general, in Python, operators and functions will try to execute no matter what type of objects are passed to them. But they might do different things depending on the types, like plus adds numbers and concatenates strings. And if there's really no sensible way to interpret addition, then it'll throw an error and say, you can't do that. I don't know how to interpret that overload. OK? OK. So now this is an important thing in Python compared to many other languages, for those of you who are familiar with them. All variables in Python are references to the objects they contain. Assignment does not make copies. Okay? So what does that mean? So here, I'm creating an array, A, and now I'm setting a variable B to refer to the same array, 1, 2. So B is array 1, 2. And now, in this next box, this is going to set the first element of the array to 0. Also, all arrays are 0 indexed. All lists are 0 indexed in Python. So let's take a look. There it is. It set the first element of the array to 0. So what is this going to do? What's it going to display? Huh? So who thinks it's going to be 1, 2? And who thinks it's going to be 0, 2? OK, wait, let me try that again. Who thinks it's going to be 1, 2? Who thinks it's going to be 0, 2? Who thinks not at all? Because that was a sizable fraction of the room, judging by the response to that question. That was a dichotomy. There's 2 possible outcomes, and you have to, like, you know, come down somewhere, or else the fence will hurt when you land on it. So, it scrolled. No, it didn't execute. OK, here we go. Wow, it's thinking really hard. What is going on? That is strange. That is the third option. Good point. I retract my insults. What is it doing? OK. Well, so it should be 0, 2. Maybe it will respond. Try interrupting the kernel and doing that again. Did my kernel crash? How odd. Ah, there it is. OK. Array 0, 2. So what happened? The point is that in this code, this is creating an object in memory, which is that array. And it's just assigning a reference to that array here. This is assigning the reference to the same array, which means that if I change it here, it's changed in the original place. There's only one array, 1, 2. They just 2 variables refer to the same thing. And that is true of every variable in Python. So in some programming languages, you can have what's called, well, you can have variables that are references or pointers or kind of analogous. Or you can have variables which just like are the thing, and if you have an assignment, it makes a copy. That does not exist in Python. Everything is a reference. And once you wrap your head about that, it means you don't have to remember that there's 2 possible ways it could behave. There's only one. Yeah? How do you copy? So you can do C equals A, I think A dot copy. And we'll take a look. There's C. And then C1 is equal to 7. And C is 0, 7. But A is still 0, 2. There is a mechanism to copy, but you have to do it intentionally. Okay? Which actually is often, if you think about it, what you want. You don't want the thing to copy, especially if the object you're playing with is very big. So in a lot of computations, if you like doing quantum mechanical computations with exact diagonalization, you end up with some very big matrices, very big vectors, and you don't want to make unnecessary copies because you might be memory limited. Okay? Yes. So Python handles memory management. The way it does so is by a method called reference count garbage collection. So I can't really demonstrate this. I can just tell you what it's doing. If you have this array 1, 2 currently has 2 references to it. If I were to forget the references, I can delete the variables, or they go out of scope. Del A, del B. Now I can't refer to that array I created anymore. They're gone. And the array object, every object in Python actually has a reference count. So when I did that, the reference count went from 2 to 1 to 0. And when the reference count goes to 0, Python knows the code can't refer to the object anymore, and it will deallocate it. So it does automatic memory management. Does anybody see the problem with that method? It's a very simple method. It works pretty well in practice, but it is possible to have big memory leaks. Circular references. So if you create a structure where there's a variable which has some field which refers to another object, which refers to another object, which eventually refers back to itself, and then you forget any reference to that ring of objects, each of them still has a reference count from the one that pointed to them, and then it won't get collected. So if you're doing code which has kind of lots of references in kind of a graph structure, you need to be careful that you don't create loops if you want to deallocate. If you're never going to deallocate, it doesn't matter. Any other questions about that, since we're diving into some more technical details? Sorry, say it again? The reference thing is done so that you, as the programmer, don't need to think about memory management unless you really have to. That's right. So it's trying to automate the allocation and deallocation of memory, which in many languages is done manually. OK, so let's move on. Moving right along. What are the types of objects? So the basic types that are built into Python are various numeric types, integers, floating point numbers, like 1.2, complex numbers. It's a built-in type in Python, quite convenient. Unfortunately, I guess they were engineers or something, because the square root of -1 is a j, not an I. But there it is. If you write 1j, actually another important notational point, you have to have, it won't recognize, if you just wrote a j, it would recognize that as like the variable j. You have to have a number before it that ends in j, and then it knows it's supposed to interpret it as square root of -1, as an imaginary number. So those complex numbers are built in. Boolean is a built-in type, true and false. Strings, in quotes, like hi. Then there are a bunch of composite types, which are actually basic types in the Python language. So there's something called a tuple, which is written with parentheses and has objects separated by commas. The things in there can be any kind of Python object, so 2, 7 high is OK. It's an ordered collection of those objects. And after you create it, you can't change the items you put into it. So I couldn't, after creating a tuple, change that 7 into a 6. I'd have to create a new tuple. So that's what's meant by this comment here, that it's immutable. It's some obscure term, but that's what it means. I can't mutate it. Lists look a lot like tuples. They have square braces instead of parentheses to create them. Again, they can contain any kind of Pythonic object. It's an ordered collection of objects represented by square brackets. And it's mutable. That means you can add, remove, change, do whatever you want to the list after you create it. You can append things to the end. You can change elements in the middle of it, et cetera. Okay? Then there's a basic type, which is called a dictionary, also known as an associative array, which, if you think of a list as being a thing which maps an integer to an object, like this one takes the integer 3 and maps it to the string hi, dictionaries take whatever thing you want and map it to another object. So there's a set of keys, in this case the key hi, it's a string, and they have values, 3, which can be any other object. That's a basic type in Python. That allows you to build complicated composite data structures just from these sort of simple associative arrays, dictionaries. Okay? We're going to go through these in more detail in a minute. And functions are actually objects in Python. So you can pass functions around like any other kind of data type. And then you can call them even though they were passed in and so on. So that's also something not supported in most languages of an earlier vintage. Okay? It allows you to do some amount of what's called functional programming. We'll go through this in more detail today. The common scientific types, which we'll get to in more detail tomorrow, are NumPy arrays. They are just like lists in that they are ordered collections, but all entries have to have the same type. So a NumPy array is an array of floats, or it is an array of integers, or something like that, and that allows them to be much faster than the general purpose lists. Okay? And that's what you're going to want to do most of your scientific computing with. Sparse arrays, which are arrays which have a lot of zeros in them, are represented by all kinds of special types. This pandas data frame I mentioned is a high-level table, a bit like an Excel spreadsheet. Okay, I could make a much longer list of scientific types. The most common are the arrays. These are used everywhere. Okay? Everything else is a little bit more application-specific. All right? So let's keep going. We are going to walk through the numeric types. As I said, there are 4: integers, floats, complex Boolean. Let's go through. If I set a equals 4 and I look at the type, it's an integer. If I test c equals 4 dot, it's a float. If I make something with that complex j, it's a complex, 1.5 plus 0.1 j. The real part is accessible, a dot real. The imaginary part is accessible, 0.1. So the imaginary part is a normal float. If I make this flag 3 greater than 4, 3 greater than 4 is a comparison. It's going to return true or false, and it's false. The type is bool. Type of true is bool, right? And I can force a particular type by, in this case, that 1 is an integer, but if I wrap float around it, it will become a float and display with a 1.0. Okay? The machine precision, I guess it's floats are all doubles. And complexes are 2 doubles. Now, there's another question. How big is an integer? So what's the biggest integer you can represent? Does anybody know? So actually in Python, in pure integers, somebody had the right answer. It's actually unbounded. If you try to represent an integer larger than the native 64-bit one, which would be something like 2 to the 64 or 2 to the 63, it will internally, without you having to do anything, actually allocate more bytes to represent a longer integer. And so integers in pure Python are, if you want, arbitrary size. But in NumPy arrays, which is what you'll mostly use for scientific computing, you need to fix the size of the integers you're using. So if you have 64-bit integers, you have 64-bit integers, and they're not going to get bigger just because you try to assign something bigger. Okay? But the core integer language, core integers in the language are arbitrary. So in Python, this is important. If you divide two integers, you get a float. Okay? 3 divided by 2 is really 1.5. In many languages, that would give you 1. If you divide integers, you get an integer. In Python, it is a float, so it's 1.5, and which is the same as if you divided two floats. If you want to force integer division, which is really getting the floor of the division, right, the largest integer less than the actual quotient, use this double slash. Okay? Good. Now, there's another basic type. Let's move on. Any questions about numbers? No? Nobody wants to know how to construct them in ZF set theory or something like that? No? Okay. Nobody cares about my stupid math jokes. Okay, that's fine. So the next basic type is a string. They are immutable sequences of characters, which means once you create them, you can't change them in place. You have to make copies of them to make changes to them. It's okay in practice. Literal strings can be written with single or double quotes. Multi-line strings can be written with triple quotes. And raw strings are useful for embedding stuff with backslashes. So let's see how that works. As we already saw, these two hello strings are the same, even though I wrote them with different quotes, because the quote is just introducing that it's a string literal to follow. They both say hello. If I use triple quotes like that, then Python will just include the new line character, which is saying that's a multi-line string, inside the string. And so A now has this funny, when I display it that way, \n there, which many of you will recognize is computer speak for new line character. And if I print \n_u, I don't know if you can tell, but this is a new line. There's extra white space there, followed by a u, right? \n meant new line. But there's this thing called a raw string, which is really just a way of inputting a string. So if I put an R before that first quote, then when I put that \n, it won't interpret it as a new line. It'll just be a string, \nu, okay? And there it is, \nu. Why am I sort of belaboring this? This is very useful if you are putting mathematical formulae into your figure annotations, labels, and things like that, and you can write them in LaTeX math. Like, as you can just put a label on a figure in Matplotlib, which has integrals and whatever, written in pure LaTeX. But in order to do that, there's a lot of backslashes, and you need to use these raw strings, or else they won't be interpreted correctly. Okay? So here is the first bit of a famous float, 3.1415, which I've assigned to the variable a. And there are various ways to convert that into a string in order to print it with different kinds of formatting. So a simple one is just convert it to a string. Str a gives me back that, and that plus was concatenation. There is, I don't want to go into this in too much detail. These examples are here to make you aware of them more than me explaining them in this case. Here, this is called sprintf style string formatting. That %1.2f means put a float there with 2 decimals after the point. And the %s means put a string there, and then I have this symbol % there, and then a tuple with the first thing that goes in there and the second thing which goes in there. So if I execute that, I get blah 3.14 high. And then there's this new style string formatting, which is even more sophisticated and gives you a lot more control about how it formats. I'm not going to explain it other than give you the example and say, go read the documentation if you really want to use it. Okay? Okay. Lists. So these composite objects are basic data types in Python. So Python works, they're very efficient, actually, considering how flexible they are. Lists are ordered collections of arbitrary objects. They're efficient maps from index to values. They're represented by square brackets. You can change their contents after they're created. It takes time of order 1 to look up an entry at a given index, change an item at a given index, append or remove from the end of the list. So make the list longer or shorter if you're changing at the end. It takes time of order n to find items by value if you don't know where they are, so you have to search through the thing. Remove items from near the beginning of the list, because then you have to move everything else up. And it's actually stored in memory in just a contiguous sequence, so it has to shift things. So that takes time of order n. We'll talk about slices more in a minute. And lists, like all things in Python, are zero indexed, which means that the first item in the list is at position 0, and the last item is at position n-1, where n is the length of the list. What does that mean? Takes time order 1 and takes time order n. I just wrote it there and sort of casually kept talking. Yeah, I don't know. Right. So this is an important concept, the runtime of an operation as a function of how big the object is I'm doing the operation to. And you generally want things to have as low a power of n, the input size, as you can possibly get. And that is going to be more important than almost anything else when you're trying to implement efficient numerics. So here is already the beginning of why you would want to know these things, why I put it up front here. Looking up an entry to give an index, I just give Python, say I want the third entry, and it knows exactly where that is in memory. So it doesn't depend on how big the list is for it to find the third item. But if I want to remove an item from near the beginning of the list, that means that I need to, say, take out the second item and then move the third through nth items over, which means I have to actually go through and, or the computer goes through and copies them over one step at a time. And it'll do that very quickly. It's not that Python is doing that in some stupid slow way, but it still takes a time which scales with the length of the list. And so it's not something you want to do lightly. It will make your algorithm slow when you start getting very big lists. Okay? Then you might want to rethink what data structures you're using. That's why I'm talking about it. Okay, so let's play with it. We're going to create a list. The days of the week are Sunday, Monday, Tuesday, Wednesday, Thursday, Friday. So what's this one going to do? Sunday. What's this one going to do? Tuesday, Wednesday, Thursday. So this is called a slice. And a slice in Python is introduced by these colons, which appear in the square brackets there. This is a slice from 2 to 5. And in Python, slices are always inclusive at the bottom and exclusive at the top. It's like a half-open interval, right? Wait. Okay, it's a half-open interval. And so this is including the second, but remember it's zero index, 0, 1, 2, so Tuesday, third, fourth, and excluding the fifth. Okay? These are important that you can slice quickly. If I put in -1, if I use a negative index, it just refers from the back. So this is the last element of the list. Every other day, so this is a fancier slice. If I have a slice with 2 colons, 0, colon, -1, colon, 2. So 0 is the first element, -1 is the last element, 2 is a step. So it means that this is going to be every second element from the beginning to the end. And indeed, we see Sunday, Tuesday, Thursday. There it is. Sunday, skip a step, Tuesday, Thursday. If you want your slice to go from the beginning to the end, you actually don't have to put a number there at all. You can just leave it blank. So colon, colon, 2 is implicitly from beginning to end in steps of 2. Yeah? Sorry, say it again. What's the reason to use? Minus, that minus? Yeah. No, it's not periodic, but -2 is the second to last. -3 is the third to last. So if you want to probe things which are towards the end but not quite at it, -2, -3, right? You find becoming familiar with how slices work actually is extremely useful for all kinds of things. And all of these little details, like, oh, I can go to the end minus something, actually is very useful. But that's it. -1 is the last element, -2 is the second to last element, and so on. So you can read it as n minus 1, which is the last element because it's zero indexed. OK, so of course, at least a few of you noticed that we left out a day. How would we have figured that out if we were debugging? We could look at what we were doing, but that's too hard. So one thing we might have noticed is that if we probed it in some way, we would get 6 instead of 7 for the length of the list, right? And then we go, I left something out. What is the bug, right? And then I'd go, aha, Saturn has been left out. So I can add Saturday to the end with this append. And now, there he is. Saturn has returned. And we might also want to dress down on Fridays, so we can set Friday to be casual Friday. And now, here's our days of the week: Sunday, Monday, Tuesday, Wednesday, Thursday, casual Friday, and Saturday. And indeed, the length is right. Now, we can do a lot of things with lists. Let me just show you one useful thing. We can sort the list in place just by calling .sort. How do you? You have 3 Saturdays. OK, let's see. So first, we'll look at this days of the week, and we see how has it been sorted, and then we'll do that. Alphabetically, there's a fancy word for that, lexicographically. It's been sorted lexicographically, right? Also alphabetically. OK, well, let's see. So let's remember tab completion. So if we go and look at days of the week and hit tab, we would see that there are a bunch of methods on it. And one of those methods has the name remove. So if I had, for example, accidentally, tab complete, append monkey, and I even did it multiple times, and then I went, ack, there's too many monkeys in my week, right? Then I could say, how do I remove them? Days of the week, remove, that looks promising. Let's try that. And then shift tab, remove value, removes first occurrence of value. OK, well, let's try that. So I could remove a monkey. And I had 4 monkeys, and now I have 3 monkeys. So that worked. That was not the fastest way, maybe, to do it, since I happen to know the monkeys were at the end. So if I wanted to do it by days of the week, dot tab, what else might I be able to do? Pop index. Remove and return item at index, default last. Oh, that sounds promising. Let's pop it. Hey, the monkey popped out. Pop another monkey. Oops. Oh, I popped 3 monkeys. Days of the week. Ha, they're gone. All right. Pop. Does anybody know where the term comes from? Yeah, Rice Krispie treats are a pretty good source of programming knowledge. I agree with that. But in this case, it's actually push and pop. It's the metaphor of using a list as a stack of things that you want to deal with, and you push something onto the top of the list, which means the end, and then you pop it back off when you want to use it. It's the language of a stack. You can use a list as a stack like that, and it's actually efficient because adding things or removing them to the end of the list takes time of order 1. But if I wanted to pop, that's why the default for pop was the end of the list. If I wanted to pop from the beginning of the list, it would actually be slower. OK. So each item in a list is arbitrary. You can have a list of lists or a list of different types of objects. So here's a list with some strings and numbers of different types. Here's a list of lists. So here, what will happen when I execute this? What will I get? I hear some people saying the right answer. You guys clearly cheated. I know you hit Shift-Enter. No? No? You guys can interpret Python 2 now? Oh, that's great. OK, so we're going to pull out of the super list, this outer bracket, the second item. Well, this list is the first item. That list is a zeroth item, first item, second item. And then that's a list itself. So then we're going to take from that the first item, which is 0, 1. That's a 6. So did we get it right? Ha, 6. Great. OK. Any questions about lists? No? All right. So now let's talk about dictionaries. A dictionary is an efficient map from keys to values. They're represented by curly brackets. They're mutable. That means you can put entries in and out of the dictionary, and you can change the value of an entry. Yeah?
Sorry, question on lists.
Yeah.
I have a list of numbers.
Yeah.
I'm not even numbers anymore.
Yeah. Actually, it's a good question. You can take a slice. Depends a little bit what you want to do exactly. So if I have A is list range 10, I should be able to take, for example, the odd numbers. Oh, by the way, so you guys can see, A's range just returns something which gives me numbers up to 10. So this is a list of numbers up to 10. So here's that. So if I was comfortable with doing that, I could just B equals A and work with it B. I could A equals that, and now, of course, it did what you wanted. Of course, I didn't remove it in place, but because the removing in place requires moving things over, this may actually not be that different in terms of efficiency. So let's see. OK, that's actually great. So 1, 4, 5, Does anybody have a favorite number? Nobody has any favorite numbers? 42. There it is. OK. How about that? Now, how about value? If value %2 equals 1 for value in A. Oops. So for value, did I get that right? For value in A, if, there it is. Now that's a much fancier piece of notation. This is actually a way that Python allows you to filter lists in a way that's kind of legible. This is actually called a list comprehension. So this is, with square brackets, I'm creating a list. It is a list of values for each value in another list. So it runs over all these. If the value mod 2, that's a %2, it's mod, is 1, which picks out odd numbers. Okay? I wasn't planning on talking about list comprehensions, but actually this is probably the best way to do that, what you just said, if you're working with lists. It's, I hope, kind of legible, actually. Almost like English, though there's obviously a particular syntax to how to do that. Does this kind of make sense to people? Are there questions? Partly, I'm comfortable putting these things up here to show you that if you know Python, you can actually do a lot of sort of complicated things simply rather than needing to write a lot of code, right? Sure. You could do, well, I don't know, we could square all the odd numbers. We could have more complicated conditions, and we could have more complicated sources. So yes, do whatever you want. Good. More questions about that? That's a list. So you can tell because it's square brackets in the output. The list comprehension notation returns lists. There's a lot of, okay, so this will always return a list. There are some other cases where things that are iterable actually return a generator, which doesn't explicitly construct the list, but these things will always explicitly construct. That's, again, a little more advanced than I was planning to talk about. But yeah. You can also use this kind of notation to construct a dictionary, a hash table, key-value pairs, with similar, I mean, it's slightly different, but with curly braces instead of the square. Yeah? Can you what? If you don't want to have, oh, the sort, yeah, sure. But I mean, you have your own notebook up there. It's easy to find out, right? So B, A.sort, shift tab, or question mark. I can just put a question mark and execute it. And this says, oh, this has a very limited doc string. Okay, maybe you need to go to Google to get the full sort documentation. But what it's telling you down here, where it says key equals none, allows you to provide it with a key function. And I think there's, which then it would compare with the key. I don't think that there's a way to give it a comparison where it does an A-B comparison. It's that you can take the list, give everything a key, which then it'll lexicographically order by key. That usually gives you what you want. But if you want to do a comparison thing, there are other sort routines. You do a little Googling, you'll find it. Right? Okay. Now, dictionaries. So dictionaries are mutable, but all keys must be immutable, which basically in practice means keys can be strings, numbers, or tuples, but not lists or other dictionaries. And that's because once you put an item into like a key value pair into your dictionary, if later in the code you were able to change the content of the key, you wouldn't be able to look it up anymore, and it would screw up the dictionary. So you can only put types into the keys, which are sort of literal things, numbers and strings and so on. But the value can be anything. So the dictionary is unordered, but it takes time essentially of order 1, independent of the size of the dictionary, to look up a value from a key, add a key value pair, or remove a key value pair, which is quite different from the dictionary, where some of those things took extra time. It takes time of order n to find an entry with a particular value, because you just have to look through all the entries and see if the value matches. You can iterate through the entries efficiently. So you can go through them each in sequence, but that's the only way to find something with a particular value. So for example, a telephone directory is very naturally represented by a dictionary, which maps the names, Emmanuel, Francis, and Sebastian, to their telephone numbers. I suppose those are extensions on some kind of internal exchange, because it's not enough digits otherwise. And we can find Sebastian's telephone number with essentially the same notation, indexing notation, as for lists, but now we put the quoted string, which is the key there. There it is, 5578. The keys, the values, the length tells us how many entries are there, and we can check if Francis is in the telephone book. He is, with this in. And we can delete his entry, and he's gone. All right. So basic stuff you can do with dictionaries. And quite useful. Actually, all of the objects, compound objects in Python are kind of internally represented if they have, I don't know, if you have, a complex number, this isn't actually true, but we'll take it as the example. If you have a complex number, it has a real and imaginary part. And the Pythonic way that it would implement the real and imaginary part as being, themselves objects that are part of this compound thing is actually from a dictionary. So the fields are, .real and .imag actually are looking up in a dictionary associated with the compound object. So everything's implemented in terms of dictionaries. Okay, let's keep going. So basic types, tuples. Tuple is just like a list, but with round parentheses, and you can't change them after you create them. So 1, 2, 3, high, I use parentheses. But if I try to do this, it will complain. I'm not allowed to change the tuple after I create it. The empty tuple has special notation. So if you just have open closed parentheses, that's the empty tuple. And if you have a length 1 tuple, you have to put a comma at the end. Otherwise, it could just indicate you're grouping something in a mathematical expression. So these are special notation, right? And you see the difference here. With this comma, this returned a tuple, which was of length 1, whose first entry was high. Here, if I just put parentheses, this is just, the parentheses really don't matter. They were grouping the creation of a string, but that didn't matter. And so not length 1 actually refers to a string. Okay? Okay. And in fact, if I try to pull out the 0th element of that, I just get the first character of the string. Okay. Finally, I think, or just about finally for today, we'll talk about control flow. So we've talked about the basic data structures in Python. And now we want to actually think about how to make programs that do things. And so most of you have programmed, so I shouldn't belabor it, but control flow is just the way in which the order of steps is taken by the interpreter through the program. And control flow is ways in which you can cause the flow of the program to change. So that's conditionals like if, then, else, or iterations, and so on. One of the important things about control in Python is that the way Python defines a block, which is the set of statements that should be done if you do, say, this if conditional, is by indentation. White space matters. Okay? If you indent, you're going into a block, and if you go back out, outdenting, you're coming out of the block. In C, that's indicated by curly braces. In shell script, it's curly braces. In Perl, it's curly braces. In Python, there's just indentation. And so the white space matters a lot. Okay? And some people hate that. I actually think it's great because it means that you can visually see at a glance the control structure of a program just from where the lines begin. Okay? So, not to belabor it, if, elif, and else, what will this print? Or what will it do? Will it print, yep, it is? Not this one either, or not at all? Not at all. So the if 2 greater than 3 is false, so it doesn't go into that block. Then it checks else if 3 greater than 4. Nope, that's also false. So else, the default case, and it has these 2 print statements which are on the same level of indentation, and so it prints them both, not at all. Okay? For loops iterate through elements in a collection. This can be a list, tuple, dictionary, array, or any other thing which has sort of a, natural sense of having a collection of sub-objects. And that's the Pythonic way to think about iterations. You should always think of an iteration as being over a collection of objects, not just with counters going up and down and things like that. That's almost always the right way to think about a for loop. So here, what this will do is this is for I in range 5. So range 5 gives me the numbers from 0 to 4. So what will happen is this block, which is indented, will be executed with the variable I taking the value of each consecutive number from 0 to 4 on each run through the block. So it'll be executed 5 times with I going from 0 to 4, and we get crash. Boom. Blah. There it is. The cube of 0 is 0, the cube of 1 is 1, the cube of 2 is 8, the cube of 3 is 27, the cube of 4 is 64. Okay? We had that days of the week. For day and days of the week, that was a list of strings. Today is, oh, they're still in that funny sorted order. Today is Casual Friday. No, it's not. It's not Casual or Friday today. And for key in the telephone book, key's telephone number is stra-tel key, which pulls out the value, right? So I can iterate over all the keys in a dictionary with this very simple formula. Manuel's telephone number is that, and Sebastian's telephone number is that. Sometimes you do need an index. You need to know, are you on the 0th, the 1st, the 2nd run through the for loop? Notice that in these examples, like here, for day and day of the week, there is no variable telling me, there's no symbol telling me which run through the for loop I'm on. I just know what day I'm on, right? Sometimes you do need to know which one you're on, and so the Pythonic way to do that is to do a for loop over an enumeration of words, and enumerate words returns for each word a tuple, so it's a list of tuples. The tuple is 0, then the first word, 1, then the second word, et cetera. And you can see here, Python always allows you to do multivariable assignment. If I have a tuple being returned by something, then I can unpack it into 2 variables at the same time. So for iWord and enumerate words, I can get the number of my iteration and the word. Is that reasonably clear? Some people have totally tuned out. Some people are kind of tuned in. Some people have given up entirely. OK. And sorry, say that again? Yeah, so if I pass to print just a variable, which is not a string, it will try to, by default, it'll try to cast it to a string by doing str of that variable and then print it. So you don't have to manually cast most things to string, turn them into strings before you pass them to print. You only need to do it if you want to control the formatting in more detail. In this case, it's not important. All right. So a while loop repeats a block of code while a condition holds true. So this one, what will it do? It initializes. This is a little bit more like what you'd see in sort of other programming languages, where you just have counters that are changing. So here, I start with a variable set to 5. While it's positive, I bark, and then I decrement the variable by 1. So what this should do is count down from 5 to 1. There it is. OK? Okay. So functions are kind of a form of flow control. They're also a kind of object. Any code that you call multiple times with different values, you should wrap up in a function. So here's an example, a classic example. Return the square of x. Now, let's look at this function definition. This is actually something very Pythonic. So def, that's introducing, we're defining a function. The name of the function is square. Its argument, it has one argument. We're going to call it x. OK? Then I indent. This is a block. So the function is here. And there's 2 lines. What is the first line? The first line is a triple quoted string. It's just a string. It's not even a command. It's just a string. OK? In Python, if the first command or line in the definition of a function is a string, it becomes part of the documentation of the object. So because I put that string there, if I execute square question mark or I hit square shift tab, then we see down here that Python could pop up this information for me: signature square of x, doc string, that's what this is called, return the square of x, right? And then the file is in some IPython input thing, and the type is a function. So this string is the documentation string for the function. So it is considered highly Pythonic good practice to put a documentation string as the first line of any function you write, which describes in human language what your function is doing. Because then when you've forgotten all about your code sometime later, or you give it to your friend or whatever, it's already commented, and all the help is there for yourself, right? That is part of writing good code when you're doing complicated things. So once you start wrapping things up in functions, you should always put these commands. Now, of course, this function is fairly simple. All it does is return x times x. So if I square 9, I'll get 81. Here's a slightly more complicated function. I print n square x. Again, I've now got a doc string here, so I can look up the help, right? And this printed the 64, which appeared here, not as output, and then it returned the 64 as output, which is why it was printed a second time. Okay. Functions are objects, just like anything else. They have a type. So if I have square, the type of square is a function. I can assign it to another variable. So now A contains a reference to the function object that square pointed to. And I can call it. A of 5 is 25, right? So this means that I can pass around functions within my code, which is actually quite useful for a lot of purposes. Callbacks in object-oriented things, hooks. Sometimes in numerical code, you can pass in a function to another function which tells it how to evaluate the gradient, and then that function will implement a gradient descent for you, right? So that's why it's useful to be able to pass functions around. So here, I guess, is our final example of the day. I thought I included one more example, but I guess I moved it to tomorrow, which is fine. We'll stop a little early. What will this do? And I apologize, I didn't put doc strings, so you can't cheat in answering this question. What will this do? Some people look intensely like they're doing something else. Some people look mystified. Some people clearly know what's going on. So, okay, so what it's going to do, well, we can see, and then we'll talk through it. Is it prints in call it and in test, right? So how did that work? Well, I called it test. I didn't call test, I called it test. So I passed to the call it function a function. Test is a function. So then this executed here in call it. Then it called the function that was passed to it, which happened to be test. So that went here, and it printed in test. Then that returned, that came here, and then that returned. Okay. Sorry. Actually, good question. I think if you just outdent, it's enough. But I always put a return def blah, print hi. Yeah. There you go. You see my approach to Python, right? Oh, does it work like that? Oh, yeah, good, right? OK, so any questions about stuff we talked about today? Yeah? If you're using an array and you want to do like remove operations and things like that. So NumPy arrays we'll talk about in a lot more detail tomorrow. I left them for tomorrow. But they are not naturally resizable. There are tricky ways to do it. But they would be no more efficient. If you wanted to pull something out, it's also stored contiguously in memory. So if you want to pull something out of the middle, you still have to move everything over, right? So it'll be identical. So for many purposes, arrays and lists are similar. Arrays are faster because the way they're stored, they know that every entry is the same size in memory. And so they don't have to, they can just jump to things much more efficiently. That's the advantage of the numerical arrays. What's that? Can you square an array? Yes, you can square an array. I can square arrays in all kinds of ways. We will talk about it tomorrow, but OK, why not? So let's say that we had A was an array. 1, 2, 2, 1. How about that one? So I can, well, if I do A times A, that is element-wise squaring, see? And if I do A at A, can you raise it to a power 2? Sorry, I didn't understand. Oh, here, this square. Here. Yeah, but what it'll do is exactly what I just did. So if I did square A, is that what you mean? So that, because the code used a star inside, does the first version, which is element-wise multiplication. I don't know why it's so slow returning results to the notebook. But it'll be this 1441 case eventually. So that's actually, it is a good point. So in Python, it is a very, objects have types, but it's not a strongly typed system in the sense that any code, unless you explicitly put a check, is this of a certain type that you want, everything will just try to run and use whatever meaning it can for the object, for whatever functions you call. So in this case, I wrote the code thinking of x as just a number type, and I wrote x star x. For the array type, a star a does element-wise multiplication. And I have no idea why this is not returning. But the code should just work. But it'll work with that meaning, which may or may not be the meaning you had in mind. It's not the matrix square, right? It's the element-wise square. So it's something that it's, I think it's called duck typing, which is that if an object walks like a duck and quacks like a duck, it's a duck. We don't check it's a duck. We just, if the object can quack, then we'll call quack on it and move on, right? And that's true here too. Well, that's what this is representative of. There's no type checking, which occasionally leads to bugs. I mean, type checking is useful in a lot of code, but usually it just allows you to develop things faster. and then you have to be a little bit careful when things get complicated not to pass the wrong things or do explicit type checking yourself. Okay, I don't know why this thing stopped. Interrupt. Right. So I think, well, yeah, I think that's it. So I think we should just call it a day. It's been a long one. And tomorrow, hopefully, even those of you who are Pythonistas will actually get something out of what we do, which is going to be going through NumPy matrices a bit, slicing, more sophisticated slicing tricks, sparse matrices and compressed representations, and how to use those tools in Python to actually construct spin chain Hamiltonians and do a diagonalization study using both dense and sparse diagonalization, which is all actually very easy once you know the tools. So that's the plan for tomorrow, but I don't think we should start now because there's not enough time to actually get to the fun part and let you guys start playing with it. All right, thank you.